This is the first video on AC power, how to analyze an AC circuit for power. And what you're going to see is that when solving for AC power, it's a lot more involved than what it was in the DC circuits. Now in AC circuits, as you'll see, power is still V times I, but because voltage and current in an AC circuit have a phase angle associated with their magnitudes, that's what makes it a little bit more of a a little bit more of a complex topic than what you have in DC, where both the voltage and current are just numbers. So before we start into any real in-depth material on AC power, I just want to remind you of a few things we've already talked about. Remember that RMS quantity, and again RMS is noted with this tilde. RMS is just equal to peak value divided by root 2. Also, we talked about how impedance in general is a complex number, and that you can represent the components of impedance, the resistance and reactance, with a right triangle that's called the impedance triangle. Okay, so we talked about all this. And then just from trig, this adjacent side of the impedance triangle is just magnitude z cosine theta, and this opposite side is just magnitude z sine theta. We're going to be using some of this information while talking about how to analyze circuits for AC power. So first we're going to start finding what the instantaneous and average power are in an AC circuit. So we just have a very basic AC circuit here, source with impedance, and we're going to find the various powers associated with this impedance. So the voltage of the source is V cosine omega t minus theta V, and the current that's flowing in this path here and through the impedance is I cosine omega t minus theta I. Okay, so voltage across the impedance V of t, current through the impedance I of t. And we're going to let the angle of the voltage equal 0 and the angle of the current equal just some general theta. And this is just done to make the derivation that follows easier than it would be if these were, like some random values. So just like in a DC circuit, in an AC circuit, instantaneous power is just voltage times current. So if we take the two functions above and multiply them together, we will get that the instantaneous power can be written as VI cosine omega t cosine omega t minus theta. So it's just these two multiplied together with theta v equal to 0 and theta I equal to theta. Now, most people can't really visualize what two cosines with different arguments look like in a plot. So to help us visualize what this instantaneous power looks like, we're going to use a trig identity. In fact, the trig identity that I had right here on this opposite page here. See, we're going to let omega t equal alpha and beta equal omega t minus theta. Okay, so this right here, okay, this is going to be our alpha, and this right here, the argument's going to be beta. So using that trig identity, you can then write that instantaneous power can have this form, that you have VI over 2 cosine theta. See, that theta came from omega t minus theta, so the omega t's cancel out, we're just left with theta. Then plus VI over 2 cosine 2 omega t minus theta. Excuse me. And this came from just adding these two arguments, the 2 omega t minus theta. So you see, once we put instantaneous power into this form, now you can visualize, what this looks like versus time, because you have a constant. See this right here, that's just a constant, plus a cosine term. So that's just cosine lifted up by this amount. You see you have a cosine that's just riding and even though it's not drawn, it's symmetrically around that center point of VI over 2 cosine theta. So, you know, this is one way that you can, well, this is one form to show the instantaneous power, and it's a convenient form because, like I said, this plot comes right from this, that there's this cosine function sinusoid that's writing this constant amount. And also, as you know, for a symmetrical function, its average is just what it's centered on. So one equation that we have for P average is that it's just equal to VI over 2 cosine theta. Okay, so here's our instantaneous power equation, and then here's an equation for P average where these values here, the V and the I, they're peak values. Alright, but you see often in AC problems we want our voltage and current values to be in RMS values instead of peak values, and this primarily just has to do with that field equipment equipment that displays AC values, voltage, current, power, well, voltage and current, do so as RMS. So the next thing we're going to do is we're going to take our P average equation on the other page that has V and I in peak, and we're going to express this P average equation in RMS. So I just plug in for V peak that it's equal to the square root of 2 times V RMS, and I peak is square root of 2 times I RMS, and this is all over 2, and then cosine theta. So you can see the square root of 2's cancel out with the 2 below, and you can also write P average as V RMS I RMS cosine theta. Alright, so here's your expression for P average where V and I are peak values, and here's your expression for P average where V and I are in RMS. And you got to be careful here because a common error is that someone, you know, when they're first learning this, they'll use this expression and put RMS, or they'll use this expression and put peak, and they end up being off by a factor of 2. So just be careful of that. Now we can also write these P average equations differently by using what we know about Ohm's law. We know from Ohm's law that voltage is just current times impedance. So if I take this and substitute in, I can get that P average is just I RMS, it's a tilde there, I RMS squared times absolute value of Z. Now I'll explain why this is magnitude of Z coming up a little later. Okay, cosine theta. So see, I just took V equal to IZ and just plugged it up in here, and I can write P average in that fashion. Also, since I is equal to V over Z, we can also put that P average is, and this is substituting in for I here, so this can be written as V RMS squared over magnitude Z cosine theta. Alright, so these are two other expressions that we have for P average. There is also another way that you can write this here, because if you go back and look at our first page where R is equal to the magnitude of Z cosine theta, right? That's just from the impedance triangle. And see, that's what we have right here. We have magnitude Z cosine theta, so I can also write that P average is equal to I squared R. So P average has to do with the resistance of the impedance. Now, one other thing I wanted to mention before we end this video is that, remember, in DC, power absorbed by a resistor could be shown as, you know, the standard VR times IR, but also you could show power dissipated by a resistor as the current through the resistor squared times R, or as the voltage across the resistor times R. Alright, so you see, just like you have three forms of the equation to find power absorbed by a resistor in DC, you also, for P average, have these various forms. You know, if you look at the ones here for that are in the RMS values, see they're similar to these three. You know, you got a cosine theta here, where you don't in the DC case, as well as these other two forms. And then you got the I squared and V squared just like you do here, but you have Z instead of R. So there's some similarity between the three equations for power dissipated by a resistor in DC and P average in an AC circuit. Now, also, the reason why this is magnitude Z instead of just Z in both these equations here is because this theta, and in fact, all the thetas that are drawn in my notebook since we started this video, all these thetas are equal to theta Z. Okay, now I'm going to prove this later on in a later video, but just make a note. This is actually pretty important. So because this theta is the same angle as the impedance, that's why we don't include it here. That's why we just put magnitude. Because if we just had this as Z, including the theta Z, then it would be redundant since the angle's already here. Okay, the last thing is that, and this is just a definition, is that in AC power problems, cosine theta, we call that the power factor. Okay, we abbreviate it PF, and PF stands for power factor. Okay, and we're going to talk about, you know, in a future video, probably the next video, we're going to talk about exactly what's meant by power factor. Okay, so this was the first video on AC power, just some definitions, a few equations, and it'll probably be another video or two of more definitions and equations before we can get to a point to actually analyze some circuits for AC power.